Hello, class. This lesson is the second lesson in a two-part sequence on atoms, molecules, and ions. Specifically, this lesson will focus on an introduction to the periodic table and the arrangement of the atoms on the periodic table, as well as some other patterns we can use to help us when tackling things like chemical nomenclature and formula writing. With chemical nomenclature, it is not something that's usually directly assessed on the AP exam, but you will have to spend a great deal of time reading prompts and questions that have chemical nomenclature integrated in them. And if you know chemical nomenclature really well, it will just save you time and allow you to be a more efficient chemist. So let's start with the periodic table. So this periodic table, and I'm actually going to zoom out a little bit so we can see the whole thing. This periodic table is color-coded by the types of elements that make up each section of the periodic table. The first group is referred to as the alkali metals. That is group 1. That is the first column. That is everything except for hydrogen in that first column. The purple column here is the alkaline earth metals. That is in column 2A, that's group 2A. The center section are your transition metals. These ones are interesting because, as we will talk about, they can take on multiple charges and multiple oxidation states. We have the post-transition metal section, which down here to the left of the staircase, these things are mostly metals, and they also can have some slightly different oxidation states and charges from time to time. But above the staircase and to the right are all of your nonmetals. On the staircase itself is referred to as metalloids. We won't really talk about them as much, but they are referred to as metalloids officially. So as a recap, anything to the left is your metals, anything to the right is a nonmetal. Hydrogen is also a nonmetal, so even though it's on the left side, remember that hydrogen's a nonmetal and it behaves as such. This column 7A or 17, depending on the periodic table you're looking at, is referred to as the halogens, and then the last column is referred to as the noble gases. We also have lanthanides and actinides on the bottom, but we won't see those very much. Those are primarily reserved for nuclear chemistry and radiochemistry. We don't really cover those much in AP chemistry. In our previous lesson, we mentioned atomic number when we were talking about the atomic structure of things. It represents our number of protons, and it's written above the symbol in the periodic table. And I'm going to zoom in a little bit more so you can see. As we stated, metals, specifically some of their properties, they're malleable, ductile, and have luster. Most elements are metals, and metals primarily exist as cations or positive ions in a sea of electrons. When we talk about metallic bonding later on this year, we'll show you what that looks like. But because of the sea of electrons that metals have, that allows them to be conductive and conduct electricity, which is good. They tend to form oxides, which means they react with oxygen, and they form positive cations. As I said before, it's anything to the left of our staircase. When we're talking groups or families, those are your columns going up and down. Those are things that have similar physical and chemical properties. Excuse me, I misspoke. And usually that's because of their electron configurations. We'll talk about electron configurations in a different lesson, but we will talk about valence electrons briefly here along with charges. When we're looking at periods on the periodic table, those are your horizontal rows. Everything in the same row has the same number of energy levels, or principal energy levels, I should say. So if you're thinking about the Bohr model, that's related to the number of rings, even though we know electrons don't exist as rings, but they do exist as energy levels, okay? And again, anything to the right of that staircase is a nonmetal. If we're talking about figuring out valence electrons, which is something we'll need, anything in this first column has one valence electron all the way down. Anything in the second column, 2 valence electrons. The transition metals are interesting because usually they're somewhere in the range of 2 to 3 valence electrons, but again, it's based off of their oxidation states and possible charges. Here we'll start with 3 valence electrons, and you'll notice that it says 3A, 4A, 5A, 6A, 7A. That's exactly the pattern I'm following here. So we go 4, 5, 6, 7, and 8 valence electrons. So 4, sorry. The number of valence electrons is important because of the Octet Rule, which we'll discuss with some ion formation briefly. Whenever an atom forms a cation or an anion, it will lose electrons if it's a cation in order to have a complete energy level below, or if it will gain electrons to become an anion, it will gain enough electrons so that it has a complete energy level of 8 valence. So when we think about that, we want to think about what's easier to do. Is it easier to gain a certain number of electrons, or is it easier to lose a certain number of electrons? So that's where the staircase comes in. That staircase is really important. Anything to the right of that staircase will gain electrons, and anything to the left, and that's how I remember, left loses electrons. So if we were to turn that into charges, if I had 1 valence and I lost 1 valence, everything in that first column becomes a +1 because I have lost 1 electron. Everything in the second column becomes a +2 because I lost my 2 valence electrons. Aluminum becomes a +3 because it lost its 3 valence electrons. Boron's an interesting one. We're not really sure about the charge of boron, but we could assume a +3 for now as well, even though it's to the right of that staircase. It could also have a -3 oxidation state depending on what it's bonded to. Carbon and silicon, these things are typically -4 because it has 4 valence electrons, but some of these ones down here can have +4 oxidation states. They also can have +2 oxidation states, but that's for another discussion. Anything in the nitrogen column, we've got -3, then we go -2, -1. So these are -3, -2, -1. And then our noble gases already have their 8 electrons, so there's no charge for them. You're going to want to use these patterns to help you with the periodic table, especially when we get to formula writing a little bit later on. Okay. These gray boxes are important. I'm not sure if you've paid attention to the fact that they are gray, but anything that's in a gray box in these lessons are things that are important and you should memorize. So you need to know the names and locations of those groups on the periodic table, specifically the alkali metals, the alkaline earth metals, the halogens, which are called halides in ion form, and then our noble gases. When we're talking chemical nomenclature, there are different types of cations. As I've been mentioning, some can have a single charge and some can have multiple charges. I'll also use the term oxidation state when referring to charges. That is along the same lines. We'll talk oxidation states in a later lesson and what that really means, but I am using those terms interchangeably for right now, even though they have a slightly different meaning. So as you see, and we just talked about, our type 1 cations are things that have only one kind of charge. So anything in green forms one kind of charge. Even some of these things that are normally in the transition metal territory. They are silver, cadmium, zinc, gallium, and aluminum. Those ones specifically form one type of charge, while the other transition metals can have multiple types of charges. With our monatomic ions that are negative, monatomic anions, I should say, and really phosphorus should be here because we use phosphorus a lot. Those only form one kind of charge, and you can use the column trick that we discussed previously to help you figure those out. So when you name positive ions, you just take the name and then tack the word ion onto it. So Al3+, for instance, is the aluminum ion, or aluminium, depending on which spelling you're using. Calcium 2+ is referred to as the calcium ion. When we're referring to type 2 cations, since there are multiple possible charges and oxidation states, we need to use Roman numerals to tell us the charge. So you'll see copper, for instance, has a plus or a +2. In this particular example, I'm using the copper 2 ion because it's a copper 2+ charge. If I was referring to the copper one ion, that is referring to Cu+. So you do need to use Roman numerals to tell the charge for transition metals only, things that are in that type 2 cations. Now, there are some exceptions, like I said, silver, cadmium, zinc, gallium, and aluminum. You do not need to use Roman numerals for those because there's only one kind of ion. The whole purpose of Roman numerals is just to tell which charge we're dealing with when we're dealing with it. In our last lesson, we mentioned polyatomic ions briefly. We're going to talk more about those in a few minutes. I should mention that there's one positive polyatomic ion that we're going to deal with a lot, and that's the ammonium ion. And that is NH4 with a 1+ charge. That is a covalently bonded molecule. So if I'm drawing a Lewis structure, looks like this, and the entire thing has a 1+ charge. So it functions as a cation because of that charge, but is actually a covalently bonded molecule. When dealing with negative ions, we have to use a different kind of nomenclature because there's a nomenclature system that changes the endings to IDE. So we briefly mentioned the halogens become the halides. Similar when you're naming individual anions, you have to change the ending to IDE. So when we're looking at something like carbon, carbon becomes the carbide ion. Nitrogen would become nitride, phosphorus becomes phosphide, etc. It's not always cut and dry how they determine the roots. A lot of times there's confusion with phosphorus because you would think, oh, I would just cut off the US and I would get phosphoride. But no, that would be incorrect. Same thing with nitrogen. People think you would cut off the gen and it would be nitroide. No, that would not be the case either. So simply put, you should memorize the names for your anions: carbide, nitride, phosphide, oxide, sulfide. The halogens are easiest because the INE becomes IDE, fluoride, chloride, bromide, iodide, and hydrogen, if it has a negative charge, can become a hydride. When we're looking at polyatomic ions, you just name polyatomic ions based off of the name that they're given. So NO2-, for instance, is the nitrite ion, and SO4 2- is the sulfate ion. Now, polyatomic ions are something you need to memorize as well. This entire table is worth memorizing, okay? And when I say memorizing, the charges for the anions over here, you don't need to memorize these because you can use the periodic table based off of the columns to figure them out, but you definitely need to know how to write the ion name appropriately. When it comes to polyatomic ions, however, these are not going to be on a periodic table. These are things you need to memorize both the name, the formula, and the charge for. So I suggest making flashcards, grouping them together, and using some rules to help you figure them out. Now, a couple of these I have starred on here because there are additional polyatomic ions that fall under that particular root name and family. So most of the polyatomic names are considered roots, and it's based off of this ATE ending. If it ends in 8, that's considered the normal amount of oxygen for that particular family. So nitrate, for instance, is NO3. And then we saw above, we had nitrite, which was NO2. Both of them had a 1- charge. The ite ending simply means there's one less oxygen than the 8 ion. And that applies to all the ones that I have starred on our list here. So as you follow along, make sure that if you have nitrite, that's one less oxygen; chlorate, one less oxygen than written here; sulfate, one less oxygen than what's written here; and phosphate, same thing, one less oxygen than what's written here. With the chlorate family, there are actually 4 polyatomic ions in total. There's perchlorate, chlorate, chlorite, and hypochlorite. And the per and hypo prefixes just add or remove an additional oxygen from our base. So chlorate had 3, perchlorate therefore must have 4 because it's one more than normal. Chlorite is one less than chlorate, so that would be ClO2. Hypochlorite would be ClO because it's one less than chlorite. It's kind of like a systematic way of identifying the number of oxygens in the naming system. As I mentioned before, when ate and ite changes the number of oxygens, the charge stays the same. So if you memorize the charges for those main groups I mentioned above, then you will also have memorized the names for the ites and the perchlorate and hypochlorite ions as well. Okay. And my example here, phosphate is PO4 3 minus, phosphite is PO3 with a 3 minus. So they still have the same charge. When we name ionic compounds, both type 1 and type 2, you write the cation name first, so just the regular name from the periodic table, and then the name of the anion with the IDE ending. With type 1, you don't need Roman numerals, but type 2, you do need Roman numerals. We don't need any prefixes when we name ionic compounds because prefixes are used when we're dealing with covalent compounds, which we'll talk about shortly. So here's a nice little flow chart. Is it a binary compound? The word binary meaning two. Does it have two elements in it? If the answer is yes, is there a metal present? If there's no metal present, we're going to use type 3, which is prefixes, which we'll talk about a little bit later. If there is a metal present, then you have to determine if it's type 1 or type 2. If it can form more than one cation, meaning it has more than one charge, then you need to use Roman numerals with that cation. If it is type 1, you just write it as is.